The fifth problem from the homework tells us we need to find the volume of a solid that's formed by rotating the region bounded by y equals 0, y equals the square root of x, and y equals x minus 2 about the x-axis. So the first step is that we should probably get an idea of what that figure actually looks like. So let's start by thinking about a graph. If we were to think about our curves, y equals 0 corresponds to the x-axis. Y equals the square root of x is the half of a parabola opening to the right. So it looks like this. And y equals x minus 2 is a line with slope 1. And it has a y-intercept, negative 2. It looks something like that. And so as we're trying to find out what the bounded region is, we should have an idea now by thinking about the shaded region that excuse me, we imagine that region is rotating around the x-axis. So let me just quickly sketch that in as well. We want to rotate that about the x-axis. Now there are two different behaviors. So you notice here, if we were to think about regions, that little rectangle, if it were to rotate around the x-axis, would actually create a circular disk, whereas if I were to think about this little rectangle that has a distance from the axis, if it were to spin around, it's as though we get only part of a disk. And so as we calculate the volume, we'll need to take those two ideas into account. Okay, so the entire figure, if we were to imagine rotating it, we get a shape that looks like a parabola on the outside with a cone knocked out of the center. So inside here we still have circles, except that's been sort of drilled out of the inside. Now there are actually two ways to calculate the volume. One is to calculate the volume of this paraboloid shape, and then to calculate the volume of the cone that gets taken out, and we'll subtract. So that's one way. That's a fairly direct way. The second is to actually calculate the volume by thinking about two regions and using these two different shapes, the solid flat disk versus this other shape that looks sort of like a washer. Okay, so one of the key things that we need to do is we need to find out where these key points are. So we need to find a point of intersection. So let's find out where the curves meet. If I'm interested where y equals 0 and y equals x minus 2 meet, I'm going to solve the equation x minus 2 equals 0 and get x equals 2. Alright, if I'm curious where the square root function meets the x minus 2 function, I'll solve that as well. Notice that this is going to require squaring both sides. So the square root of x squared is x. X minus 2 squared is really x squared minus 4x plus 4. Let's move that x to the other side, and we get x squared minus 5x plus 4 equals 0. And if I factor that, I get x minus 4, x minus 1 equals 0. Two answers, x equals 4 and x equals 1. And yet there's only one point that actually has an intersection. So I just want to point out the other root is called an extraneous root, and it would be what you would find if you took this parabola and it actually came back, the rest of the parabola that we don't see would intersect at x equals 1. Alright, so the second point is at 4. Alright, so to calculate the volume, what we want to remember is that we have circular cross-sections. So if I were to imagine making a cut of my shape in this vertical direction, I get a bunch of circles. And so this would correspond to creating a partition along the x-axis. And so I could approximate the volume by thinking about the kind of volume I would get from a single rectangle. And so that rectangle would give me a disk, and the height of the rectangle gives me the radius. And so for every x value, xk, the radius of that rectangle is going to be the square root of x sub k. And so the area is calculated as pi r squared, where the radius is given by the square root of xk. And so the area of a single slice is going to be pi times the square root squared, gives me back x sub k. Now, to calculate the volume, I need to take that area of cross-section and I need to multiply it by the thickness, delta x. And so the volume would be approximated as the sum of pi xk delta x. And I want to take a limit of that because I want to have an exact calculation. And this is where we get our definite integral. We'll integrate from 0 to 4 of pi times x, that's pi r squared, times a little thickness, the delta x becomes dx in the integral, and the fundamental theorem of calculus says don't bother taking the limit, instead find an antiderivative. Pi halves x squared, and we'll evaluate that between 0 and 4 and subtract. So we always evaluate at the end point first. Pi over 2 times 16 minus pi over 2 times 0. Okay, so we get 8 pi. And so this is the volume of the paraboloid, but we haven't subtracted out the little cone that we need to take out. And so the actual volume is going to be 8 pi minus the volume of the cone. And we have two ways we could do that. Notice that the cone is going to have a radius given by this height. So that height at 4, whether I use this formula at 4 I get 2, or this formula at 4 I get 2. So the radius of the cone is going to be 2. The height of the cone is going to be 4 minus 2, so that's also 2. And so what I get is I'm going to have a cone with a radius of 2 and a height of 2. And so the volume of the cone is 1/3 pi r squared h. And so that's 8 pi over 3. So my final volume is 8 pi minus 8 pi over 3, which happens to be 16 pi over 3. Now the other way to do this problem is to think about it in two sections. First, think about the interval from 0 to 2, where we actually have a nice paraboloid all the way. And so there we can calculate the volume of the first piece as an integral from 0 to 2 of the area of cross-section, which is pi r squared times the little thickness, dx. And then we integrate from 2 to 4 the area of cross-section, which happens to be a big circle with a little circle taken out. And so this area of cross-section is going to be pi big radius squared minus pi little radius squared. That pi factors out, and so I get pi times big R squared minus little r squared. And so my integral is going to be pi times the big radius squared minus the little radius squared. There's the area of cross-section times the thickness that I add up. Okay, so the first contribution comes from pi r squared. As before, the radius goes from the axis to the curve square root of x, and so I'll square the square root of x and integrate. On the second piece, the larger radius is the square root of x, and the smaller radius is this formula x minus 2. Alright, so my YouTube time limit is about to expire, so there's my big radius. I'll square the square root. I'll square x minus 2 squared. I'm going to do some algebra and show the answer. So first, I'll simply square the square roots. I'll expand x minus 2 squared and subtract it. So notice that I changed the sign in each of those three spots. Then I'll take my formula for my integrals and find antiderivatives. So pi over x has an antiderivative. This polynomial, I'm going to combine x and 4x to get 5x and integrate it. X squared integrated is negative 1/3 x cubed, minus 4 integrated is minus 4x. And now I'm going to evaluate it at the endpoints and subtract. And so we evaluate the first antiderivative at 2 and at 0, and the second antiderivative at 4 and at 2. And so I get 2 pi. These terms simplify to 8 pi over 3. These terms, when I subtract them, becomes adding another 2 pi over 3. And so I get a total of 10 plus 6. Is that right? 16 pi over 3. And that's the same answer we got before. And so that is the volume of our solid.